Hello friends, today we will see the topic photochemistry. In your syllabus we have a topic of photochemistry. Now we will see the topic photochemistry, its weightage and all things about our syllabus. Photochemistry, it is the branch of chemistry. It is the branch of chemistry which deals with rates as well as mechanism of chemical reactions which involve radiations. Means photochemistry is the branch of chemistry which deals with rates as well as mechanism of reactions taking place in presence of light. Generally in photochemistry which study the reactions takes place in presence of light radiations from 2000 angstrom to 8000 angstrom, generally UV visible range. Okay, all types of chemical reactions, whatever the chemical reactions, for example substitution reaction, elimination reaction, as well as decomposition reaction, synthesis reaction, all reactions are involved in photochemistry. Photochemical, all reactions involved in photochemistry. Now, what is the difference between general reactions and photochemical reactions? General reactions means they are called as a thermal reaction or they are called as a dark reactions. The reactions, usual reactions which we do in our laboratory, the reactions which are not influenced by presence of light, presence or absence of light, they are called as dark reactions, or they are influenced by temperature, concentration, presence of catalyst. Such reactions are thermal reactions or dark reactions which are not influenced by presence or absence of light. They are called as a thermal reactions or dark reactions, while those reactions which are induced, started, influenced by light, called as photochemical reaction. Okay, now we will see the difference between dark reaction and photochemical reaction. What is mean by dark reaction and what is mean by photochemical reaction, and what is the difference between them. Now if we consider a thermal reaction or dark reaction, in this reaction the energy of activation, we call it as a EA, energy of activation, it is provided by collision of molecules. It is provided by collision of molecules, collision of different reacting molecules. A molecule collide with B molecule, and then only there is a reaction. In dark reaction, energy of activation is provided by collision, while in case of photochemical reaction, the required energy is gained by absorption of quantum of energy or photons. By absorption of light photons, this energy of activation is provided in photochemical reaction. The second difference is that there is large change in rate. There is a large effect of rate on this dark reaction with change in temperature. In case of dark reaction, There is a large effect on rate with change in temperature. If we increase the temperature, rate of reaction increases in case of dark reaction, because temperature is nothing but the average kinetic energy. As kinetic energy increases, the collision between molecules, collision between molecules becomes effective collisions. More collisions becomes effective collisions. While in case of photochemical reaction, there is no such effect of change in temperature. Or if there is a if there is effect of change in temperature, then it is a temperature part of reaction. It is not a photochemical reaction. In case of usual photochemical reaction, there is no effect of change in temperature. Okay. Third factor, third distinguishing factor is that in case of dark reaction, change in free energy gives free energy is always negative. In thermodynamics, you know this. If there is a change in free energy delta G, if delta G is negative, then and then only the reaction is a spontaneous reaction. Okay, but in case of photochemical reaction, this delta G may be positive or negative, because the energy is transferred from light energy to chemical energy. Okay. Next differentiating character, fourth difference between photochemical and thermal reaction is that in case of thermal reaction or in case of dark reaction, generally on increasing temperature, all molecules are increased in energy. All molecules are increased in energy. Their energy is increased. Kinetic energy of molecules is increased on increasing temperature. That's why it increases. But in case of photochemical reaction, what happens? Very few molecules absorbs radiation, and they get excited, get transformed into higher energy, and that's why the reaction will take place. Okay. And next factor, in case of thermal reaction, the rate is almost doubled by 10 degree rise in temperature. Rate is almost doubled by 10 degree rise in temperature. While in case of photochemical reaction, there is no such effect of change in temperature, or very few or very small effect of change in temperature. Okay. This is the difference between photochemical reaction and thermal reaction. Now, before starting actual photochemistry or photochemical reaction, we must know some laws of photochemistry. Okay. Now, when light is incident on a certain reaction mixture or a certain system, from that incident light, if suppose I0 is the intensity of incident light, from that incident light, some light is absorbed by the molecule. Some light is transmitted by the molecule from the system, and some light is reflected, and this generally this reflected light is neglected. its amount is negligible. Only we consider absorbed radiations and transmitted radiations. Okay. Now, if we consider the first law of photochemistry, it is also called as Grothus-Draper law. Grothus and Draper's law. Very simple statement. Grothus and Draper's law. It states that only those radiations which are absorbed, only those radiations which are absorbed by a reacting system are responsible for producing chemical change. Yes, means transmitted or reflected radiations are not responsible for chemical change. This is the first law of photochemistry, also called as a Grothus-Draper law. What is the statement of Grothus-Draper's law? Only those radiations which are absorbed by a reacting system are responsible for producing chemical change. Other radiations which are not absorbed, that means transmitted radiations, or we can say reflected radiations, these radiations are not responsible for any type of chemical change. They are not factors affecting on the photochemical reactions. Only absorbed radiations are responsible for chemical change. This is a very simple law. Then second law of photochemistry. It is the Lamberts law. Lamberts law. Okay. Now see the statement of this Lamberts law. What are the conditions for law and then actual law? Now we will see the statement. When a beam of monochromatic radiation, we must have a monochromatic radiation. Mono means single, chroma color. Single colored radiations or having single wavelength, they are called as monochromatic radiations. When a beam of monochromatic radiation is passing through a homogeneous absorbing medium, homogeneous absorbing medium, these are the conditions for this law. When a beam of monochromatic radiation passes through a homogeneous absorbing medium, then actual law, the rate of decrease in intensity, rate of decrease, negative, rate of decrease in intensity of incident radiation is directly proportional to intensity of incident radiation. Is directly proportional to intensity of incident radiation. Okay, this is the statement of Lamberts law. Let us state once again. When a beam of monochromatic radiation is passing through a homogeneous absorbing medium, then the rate of decrease in intensity of radiation with thickness of absorbing medium is directly proportional to intensity of incident radiation. Means minus di by dx. This is the decrease. This negative sign indicates that decrease in intensity of radiation with thickness of absorbing medium is directly proportional to I, intensity of incident radiation. Okay, just simplify it. Minus di by dx is equal to some constant k into I. Okay. Now rearrange this equation. Minus di by I, take similar terms to one side. Okay. Minus di by I is equal to k dx. Now integrate this equation between the limits. When I is equal to I0, then x is 0. And when I is equal to I or IT, whatever, then x is equal to x. Means integrate this equation between I0 to I when the value of x is 0 to x. Means if we consider this thickness of absorbing medium as x, then suppose this is the incident radiation. We are integrating this equation between the limits I0 at the just entry of this reaction medium or the entry of this system. At this point x will be 0 and up to the radiations which are coming out. Here intensity of radiation will be I when x is the thickness of absorbing medium. Okay, integrate this equation. Minus remains as it is, di by I is equal to integration k dx. K is constant, we can take out of integration k dx. Okay. Integration of 1 upon I di. It will be, yes, ln of I. Minus sign remains as it is between the limits I0 to I. 0 to x. Its integration, left side integration will be ln of I between the limits I0 to I is equal to k. Integration of dx will be x between the limits 0 to x. Okay, minus, okay, take this, apply these limiting conditions. It will be upper limit minus lower limit, means ln of I minus ln of I0 is equal to k into bracket x minus 0. Okay, therefore minus ln of I upon I0 is equal to kx. Okay, and this minus, if we replace this minus sign, it will be ln of I0 upon I is equal to kx. If we transform this natural logarithm, then log to the base 10, then what happens? It will be 2.303 into log of I0 upon I is equal to kx, or log of I0 upon I is equal to k upon 2.303 x, or log of I0 upon I is equal to a into x. This log I0 upon I, what is this I0 upon I? It is called as a opacity. Okay, I0 upon I is called as a opacity. I upon I0, it is called as a transmittance. Reciprocal of transmittance, that means I0 upon I, it is called as a opacity. and logarithm of opacity is called as a optical density. Therefore, optical density, or also called as absorbance, is equal to AX. This is the Lamberts law. And this Lamberts law is applied for solution by Beer, called as a Lambert-Beer's law. Simply you can say Beer's law or Lambert-Beer's law. Statement is same as that of Lambert's law. Conditions are same, just you have to consider solution. What is the statement then? When a beam of monochromatic radiations passes through a, conditions are same, monochromatic radiation as well as homogeneous. Instead of medium, you have to consider a solution. Okay? Then what is the statement? When a beam of monochromatic radiations passes through a homogeneous absorbing solution, then the rate of decrease in intensity with thickness of radiation with thickness of absorbing solution. Here you have to say solution instead of homogeneous substance. Okay. Decrease in intensity of radiation with thickness of absorbing medium is directly proportional to intensity as well as, for solution, it is directly proportional to concentration also. This is the Lambert-Beer's law. Same as that of Lambert's law. Okay. Mathematically, how will you write? Minus di by dx is proportional to I as well as C. I is the intensity of incident radiation and C is the concentration of solution. Okay, now state this Lambert's law again. When a beam of monochromatic radiation passes through a homogeneous absorbing solution, then the decrease in intensity of incident radiation with thickness of absorbing medium is directly proportional to intensity as well as concentration. Okay. Now simplify this and solve same as that previous equation. Di by dx minus di by dx is equal to some constant, say k dash I into C. Okay. Now if we solve this, minus di by I is equal to, say take similar terms to one side, it is equal to k x as well as concentration, not x, dx. Okay. Now again integrate this equation between the limits. You will get same equation, log of I0 upon I, you can write, is equal to k upon 2.303 C and x. Same equation, and this log of I0 upon I is called as a optical density. D is equal to, this is constant, k dash upon 2.303 is constant, we can say it is a epsilon C x. This is the Beer's law, mathematical statement of Beer's law. Optical density is equal to epsilon C x, where epsilon is the molar extinction coefficient. Epsilon is the molar extinction coefficient. C is the concentration of solution in mole per dm cube. X is the thickness of absorbing medium. Now we will define this molar extinction coefficient. There is a standard method to define any constant in equation. In this equation, if we put c is equal to 1, x is equal to 1, then d is equal to epsilon. Yes, got it? Means when concentration is 1 mole per dm cube and thickness of absorbing medium is 1 centimeter, then what happens? D is equal to epsilon. Means epsilon is D when C and X is unity. Then how will you define this epsilon? Actual statement. Molar extinction coefficient is the optical density of a solution having concentration 1 mole per dm cube and thickness thickness of 1 centimeter. Okay, this is the definition of molar extinction coefficient. These are the three laws, and we will see fourth law of photochemistry. It is also called as Stark-Einstein law. Stark-Einstein law of photochemistry. This Stark-Einstein law of photochemistry, it is also called as law of photochemical equivalence. Law of photochemical equivalence. Fourth law of photochemistry. It is also a very simple law. Okay. What is this law? Each molecule, very simple, equivalence law. Simply you can say one molecule of reacting substance absorbs one quantum of radiation. One molecule absorbs only one quantum of radiation. That is the Stark-Einstein law of photochemistry. Yes, an actual statement. Each molecule absorbs a single photon or quantum of light in photochemical primary process. Initial stage, primary process. Whatever may be the next reaction, in photochemical primary process, you can state condition initially also. What is the Stark-Einstein law? In photochemical primary process, one molecule absorbs or each molecule absorbs one quantum or photon of radiation. This is the Stark-Einstein law of photochemistry. It is also called as a law of photochemical equivalence. One molecule absorbs one quantum of radiation. Okay, means this, if we consider A, it absorbs one H nu and forms a activated molecule A star. This is the photochemical primary process. Whatever may be the reaction afterwards. In photochemical primary process, one molecule of reacting substance absorbs one photon of radiation. Okay, this is the Stark-Einstein law of photochemistry. And now the energy of radiation is given by h nu. E is equal to h nu. We know this equation. It is a well-known equation, or you can convert this as a E is equal to hc upon lambda. E is equal to hc upon lambda, where h is a Planck's constant. Its value is 6.624 into 10 raised to minus 34 joule second. In SI unit, this is the value of H, Planck's constant. Okay. Now, if we consider this Stark-Einstein law, one molecule absorbs one quantum of radiation. Two molecule absorbs two quantum of radiation. Three molecule absorbs three, four, four. It is a photochemical equivalence law. Now, one mole absorbs. No. Before that, we will go for n number of molecules. E is equal to n Hc upon lambda for n number of molecules. And if n is Avogadro's number, then what happens? It will be the radiation absorbed by 1 mole of substance. And this energy is called as the Einstein energy. Okay, means one molecule absorbs one quantum of radiation. Its energy is given by Hc upon lambda, while one mole of substance absorb one Einstein of energy, or it is given by n. You can write n a Avogadro's number, Hc upon lambda. Okay, n Hc upon lambda. And if we do simple calculations, E is equal to n Avogadro's number Hc upon lambda. This is the energy of one Einstein. One photon energy Hc upon lambda, and one Einstein energy n Hc upon lambda, where n is the Avogadro's number. You know the value of Avogadro's number. Therefore, E is equal to, we will determine, or we will simplify it. What is the value of Avogadro's number? 6.023 into 10 raised to 23 molecules per mole. Unit of Avogadro's number. Molecules or particles per mole. 1 mole of substance contains Avogadro's number of molecules. Okay. Into H. Value of H is 6.624. Some take 6.626, 624, whatever may be. Into 10 raised to minus 34 joule second. Into C, velocity of light, in SI unit, 3 into 10 raised to 8 meter per second, divided by lambda. If we do the calculations, excuse me, if we do the calculations, the value will be 1.1962. 1.1962 into calculation minus 23, 10 raised to 8 divided by lambda in nanometer. If lambda is given in nanometer, we have to convert it as we have to take in nanometer, lambda in nanometer. E is equal to 1.1962 into 10 raised to 8 upon lambda. Lambda should be taken in nanometer. The value will be, our unit will be joule per mole. Okay, and joule per molecule, you have to remove this Avogadro's number. Okay, now if we consider actual photochemical reactions, if we consider actual photochemical reaction, you can simplify this further also. E is equal to 11962 0 into 10 raised to 3. We are taking 5 digits to the right side. 1, 2, 3, 4 and 5 divided by lambda in nanometer. Or you can write E is equal to 119620 upon lambda in nanometer kilojoule per mole. We are converting it into joule to kilojoule. 119620 upon lambda in nanometer, you will get directly the value of 1 Einstein energy. Now, according to this photochemical equivalence law, Stark-Einstein law, one molecule absorbs one quantum of radiation. Then the yield of reaction should be 100%, or the ratio should be 1. If one molecule absorbs one quantum of radiation, then that absorbed molecule must react with the other reactant and it should give product. There should be a 100% yield in photochemical reaction. But in photochemical reaction, instead of saying only yield, it is written as quantum yield. It is known as quantum yield. Quantum yield means the number of molecules or the atoms, ions, whatever may be in the reaction system. Quantum yield is defined as it is the number of molecules reacting per quanta or number of moles reacting per Einstein of radiation. It is called as the quantum yield. Then how will you write this quantum yield? It is denoted by phi. Quantum yield is the number of moles reacting for each Einstein of radiations absorbed by the molecules. Okay, then it will be the ratio of phi should be the ratio of number of moles reacted or reacting in given time divided by number of Einstein absorbed in same time. According to law of photochemical equivalence, if one molecule absorbs one quantum of energy, then this ratio should be 1. Number of moles reacted divided by number of Einsteins absorbed will be equal if it is the ideal condition. It is ideal condition. This quantum yield is 1. It is the ideal condition. Phi is equal to 1. Because we know the law of photochemical equivalence, that is one molecule absorbs one quantum of radiation and that absorbed molecule may react to form the product. Okay, therefore the number of moles reacting to the number of moles Einstein, this ratio of number of moles reacting to the number of moles of Einstein absorbed in same time will be 1. But in actual practice, for only few reactions this ratio is 1. But in actual practice, this quantum yield is not unity. It may be low, it may be very low, it may be high, or it may be very high. This quantum yield equal to 1 is a rare case. In most of cases, this quantum yield may be low or may be high. We will see this why this quantum yield is very low or very high in next lecture. Okay? Okay, thank you.